Okay, dear subscribers, let us begin with a new lesson from Engineering Mechanics, Tata McGraw-Hill publication, 5th edition, written by world-renowned professors A.S. Timosinko, D.H. Young from Stanford, J.V. Rao and Sukumar Pati. And I'll take about 30 minutes to finish this video. But this time we will be not solving a numerical, we will do some theory work which will be useful for solving numerical problems from set 2.6 of the book, of this book, Engineering Mechanics. So let us begin with, it's a theory. What all will be learning during the next 30 minutes is moment of a force. And the name of the article is Moments and Their Applications. So what we'll be learning in the course of the discussion: moment of center. Moment center means the point about which a force has a turning effect. Moment of a force, which is a length. Moment of a force, the turning effect of a force. Moment center, the point about which the force has a turning effect. Moment arm, I will discuss. Then what is clockwise movement, how to take the sign convention, anti-clockwise movement, and how to take the sign convention while solving numerical problems from set 2.6 of the book Engineering Mechanics by Professor Timosinko and D.H. Young. And we shall also be learning the graphical representation of a moment. And this thing, the graphical representation of moment, which I will explain in few minutes from now, will be useful to understand the statement and proof of Varignon's theorem. Varignon's theorem, who was a French mathematician, was a professor also in France for some time, and was a contemporary of Newton also. Now, so let us begin with, it's a very important theorem. There is a system, and the system consists of many forces. So, means suppose there is a rigid body, there is a force to this side, there is a force to this side, there is a force to this side, there is a force to this side. There are many forces in the plane. Now, every force of this system has a tendency to produce some turning effect about some fixed point. That fixed point will be called as the moment center. So let us proceed further. So to produce some turning effect about a fixed point, provided the line of action of the forces do not pass through that fixed point. This will be clear to you the moment I give you examples. So wait until then, let us proceed further. The turning effect of a force on a body is called moment. The turning effect of a force on a body is called moment of that force. And it is represented as m and is the product of force and the length, where the length is the perpendicular distance from the point and the line of action of the force. I will be explaining here. Now look at this. Why I am using the word product? Because these two are not two numbers, so I am using the word product, but I am using the symbol, this cross, multiplication. Now look at this diagram. Here is a force. What is its effect about the point O? So let me draw this line like this. This force F is perpendicular to this line at this point A. Sorry. Suppose this is a thin rod fixed at O, and you are applying the force like this, such that this angle is 90. There from O to A, which I have represented as L, is the perpendicular distance of the point O from the line of action of this force F. L is the perpendicular distance from point O from the line of action of this force F. and the point O about which we are trying to find out the moment of this force, that is the turning effect of this force, is represented like as F product L. So, and the point O about which there is a turning effect is called the moment center, and this length O from O to A, which I have represented as L, is called the moment arm. It is nothing but the perpendicular distance of the line of action of the force. This is the line of action of the force that you are applying at A. So this is the perpendicular distance. Perpendicular distance of the line of action of the force F from the point O. That is the moment center. So in such a situation, this thing will have a tendency to rotate like this, as shown in the red line. That is a clockwise movement about point O. Now supposing this F is not perpendicular to this L, then there will be a different case. So let me explain that also. Now going back to the next page. Now as you can imagine here, visualize here, O is the point about which we are interested to find the moment of the force F, which is making angle theta with this line. So what we have to do is, if I draw a perpendicular here, this part from here to here will be F sin theta, provided this is theta, and this will be your F cos theta. If you draw a perpendicular, take cosine of this angle and cross multiply, you get this as F cos theta. Take sine of this angle and cross multiply, you get this as F sin theta. So what you have to visualize here is F cos theta. This is the line of action of F cos theta. This is the line of action of F sin theta. Now the line of action of F cos theta, which is a component of F, this F cos theta doesn't have a perpendicular distance from O. It is along the same line. Had F cos theta been here, then this would have been the perpendicular distance. Had F cos theta been here, then this would have been the perpendicular distance. Since F cos theta is F cos theta when joined with O, they fall along the same line. Therefore, F cos theta does not have a perpendicular distance from the point O to have its turning effect. But F sin theta, if you look at F sin theta from the point O, has a perpendicular distance from this point to this point, which I have represented as L. So F cos theta will not have a turning effect about O, whereas F cos theta will not have, but F sin theta will have, because F sin theta has a perpendicular distance from the point O from its line of action, F sin theta. Now let O is the moment center, F is the force applied at A. Let OA is equal to L. Now the same thing, what I just explained, I have written it here. The line of action of F cos theta, that is this line of action, does not have a perpendicular distance from the moment center O, at 0 perpendicular distance. So this will not have a turning effect. Whereas F sin theta has a perpendicular distance from O, which the point O is called the moment center. Therefore, the overall effect of this F can be considered as the combination of the effect of F cos theta about O and the effect of F sin theta about O. So, the moment of the force F about point O is MO, moment about point O, will be F sin theta times L, because L is a perpendicular distance, F sin theta times L, plus F sin theta times 0, because 0 is the perpendicular distance of the line of action of the force F cos theta from the point O. Therefore, I have put it as 0. So this part becomes 0. So I am left with F sin theta times L. That is the moment of this force F, which is making angle theta about the point O. The component F cos theta does not contribute. The component F sin theta contributes. Therefore, the Therefore, the overall effect of F making angle theta with horizontal is due to F sin theta only, but not due to F cos theta. So, that is what I have written here now. So there is a clockwise and the sign convention. Clockwise movement is taken as negative, anti-clockwise movement is taken as positive. But if you can interchange clockwise movement as positive, anti-clockwise movement as negative, then also there is no problem, you will be having the same answer. And in this particular case, f sine theta, the component of f, which has a perpendicular distance L from the moment center, will have a turning effect like this, that is anti-clockwise. That is in a direction opposite to the direction in which your hour hand, minute hand and second hand, they move in a clock. And then coming back to the units. Now, since it is the product of the force and the distance, force is Newton, distance is meter, therefore Newton meter. Newton meter. Now, then coming back to the important note point to be observed is, what's the difference between a torque and a moment? Torque, represented as tau, has the same unit as moment but slightly different. Torque is equal to R cross F. This is a distance, this is a force, and sine theta is just a number. So this is also Newton meter. But it is slightly different, not exactly the moment of a force, slightly different. I will explain through an example. Just let us go to the next page. Now, I have given an example here. So let us identify the basic difference between a moment means moment of a force about a given point, and torque, that is R cross F, the cross product of the radius vector and the force. Now, if you look at the first diagram, this is a seesaw you must have seen in your school days. This is already balanced, means this side is horizontal, this side is horizontal. This is the fulcrum about which it can rotate clockwise or anti-clockwise. And there is nobody sitting here, there is nobody sitting on this side, so this is horizontally balanced. Now, suppose there are two people. One person having a mass 100 kg and there is a small kid having 20 kg. They want to play this game, seesaw game, and this little boy having weight 20 kg, he wants to defeat this 100 kg man, or balance him on a seesaw. Then what he has to do, what a trick he has to play. Now his mass is given as 100 kg, so his weight, which is a force, will be m times g, that is 1000 Newton. And this little boy, which is just 20 kg mass, so if he occupies a position anywhere on the seesaw, he will have a vertically downward force F is equal to his weights mg, that will be 20 into 10, that is equal to 200 Newton. And this 1000 Newton is 5 times more than this. So what he has to do, what this little boy has to do to balance him on the seesaw. So I have a diagram here. So this is your seesaw, this is the fulcrum. This is the fulcrum about which this seesaw can rotate either clockwise or anti-clockwise. So this gentleman having mass 100 kg, suppose sits at this point at a distance, let's say 1 unit from here. So his weight is vertically downward, 1000 Newton. So this is a force. So this will have a turning effect about this point, that is equal to 1000 into 1, and that will be anti-clockwise. So that is 1000 into 1 multiplied by 1 is 1000. So to balance that, this little boy, who is smart enough and is wise also in physics, what he does, he sits at 5 times the distance. From here to here is 5 units. So this little boy sits here. His weight is acting vertically downward, 200 Newton. So this force, 200 Newton, has a turning effect about this point, will be equal to 200 into this perpendicular distance 5. So 200 into 5 is 1000. So that will be balanced by 1000 into 1. So in order to defeat him, that is to push him up, he has to increase the distance. Means if he sits at a point, beyond this point, this length will be more than 5, and his weight 200. Let's say from here to here is 6 units. So 200 into 6 will be 1200. And whereas this person is applying 1000 into 1, that is 1000. So in that case, this gentleman having a 100 kg weight will be lifted off like this. So that is how it works, the moment of a force about a given point. Now look at this diagram. This is a pot carrying milk. This is a stick. You want to churn the milk. Here is a string going around this red one, a disc, a stick. When you pull this rope to this side, this stick rotates. And if you can pull to this side, you can pull to this side. Means with your hand you pull it like this. So this stick rotates and the milk is churned. Now, so that is what I am explaining. The wooden stick rotates due to a torque, but does not turn due to a moment. So that is the basic difference between moment of a force and a torque. Now let us then go back to the graphical representation of moment. Graphical representation of a moment. Now, don't look at these red parts initially, because while I was trying to shoot this video, the video in between went wrong, so I had to reshoot it. So I am using the same paper once again, but I will explain word by word. So graphical representation of moment of a force. Now look at, let this line from A to B representing a force F to this side as indicated by this arrow, and we are interested to find the moment of this force about this point. You can consider the point here, you can consider here, you can consider here, you can consider here, you can consider anywhere you like, doesn't matter. So let F is a force represented by vector AB. O is the moment center about which we are interested to find the effect of this force about this point, that is the turning effect of this force F. So what do? I need to have a perpendicular distance, so I draw a perpendicular. So let this length is equal to y. Therefore OC is the perpendicular on the line of action of this force. This F is the line of action of this force is to this side. This is the perpendicular distance which I have taken as y. You can take it as x, you can take it as all L, no problem. So I have taken it as y because it is along y axis. Now let OC is equal to y, that is since it is along y axis. So as I just explained, how the moment of a force about a given point is calculated, that is, it is the product of the force and the perpendicular distance from the points where you are interested to find the turning effect to the line of action of the force. So moment F about point O is F product y. F is represented by the side AB, and the perpendicular distance L is nothing but from O to C. Now if you join O with this end of the force and O with this end of the force, then you get a triangle, and half base times the height is the area of the triangle. So what do is to bring area into picture. So I multiply this by 2 and I divide it by 2. So means I have not made any changes. By doing so, this becomes half AB times OC, that is half base into height becomes the area of the triangle, where the force represents the base of the triangle and the point O, the moment center, represents the vertex of the triangle. So moment of the force F about the point O in this particular case is twice the area of the triangle OAB. Twice the area of the triangle OAB. So what is the conclusion? So the conclusion runs like this. Moment of a force about any moment center is geometrically equal to twice the area of the triangle where the base is represented by the force and the vertex is represented by the moment center. Means if you are interested to find the moment of a force, if you can construct a triangle where the base is represented, where the force represents the base of the triangle, and the point about which you are interested to find the moment of the force represents the vertex of the triangle, then the moment of the force is 2 times the area of that triangle. So this concept we will use to prove the important theorem by a French mathematician that is called Varignon's theorem, or called the law of moments. The same thing will now apply. The graphical representation of moment of a force now will just apply. Now here also don't look at these red lines initially. I will explain one by one, because while shooting the video, the initial video went wrong, so I have to reshoot it again. So instead of writing all this again, I am using the same paper once again to explain you, but there will be no problem at all. So Varignon's theorem, okay, or called the law of moments. What it says, I will explain word by word. The algebraic sum of moments of all coplanar forces. Here I will take 2 coplanar forces to explain, but in fact it applies to any number of coplanar forces. The algebraic sum of moment of all coplanar forces about any moment center is equal to the moment of the resultant about the same moment center. Now look at, very simple. Now let AB represents a force P, AC represents a force Q, and as you have studied in your school days, what will be the resultant of P and Q? Taking P and Q as the 2 adjacent sides of a parallelogram, if you construct a parallelogram like this, then from A to D will be the resultant of P and Q. Means R will be the combined effect of P and Q. Means what P and Q can do together while acting in this manner, P to this side, Q to this side. If you reject Q and reject P, instead of apply P and Q simultaneously, if you apply a single force R to this side, then it will have the same effect. That is called the parallelogram law of vector addition. Here you are not interested to find the value of R. The value of R is of course found out by R is equal to P square plus Q square 2PQ cos theta square root of that, where theta is the angle between P and Q. We are not interested to find. We are interested to find something else. So what do I do? Let P is a force represented by AB. Q is a second force represented by the side AC. And I just explained how AD is the resultant of a P and Q. We are considering a point O as the moment center. We'll find out the moment of the force P about point O. We'll find out the moment of the force Q about point O, and we'll prove that the sum of these 2 moments is equal to the moment of the resultant about the same moment center O. That is what we have to prove. So Q is the second force represented by AC. P and Q are coplanar. Means they are lying in the same plane. Here they are lying in the same plane of paper in which I am explaining you. So therefore R is the resultant of P and Q, and R is represented by the side AD of this parallelogram. Now let us extend this line DC to the point O. You can consider it here, you can consider it here, you can consider it here, no problem. I have just taken this point. And the point where I'm interested to find the moment of the force P and the moment of the force Q and the moment of the force R, and then establish a relationship, how they're related to each other. So extend DC to O and let O is equal to the moment center. Now what do you do is you join from A to O and from O to B, right? And now is interesting. Let me fold this paper because of there is less space in my table to explain. So now it is interesting. Now the last part. Now look at. Now is interesting to observe. For triangle AOB, this is the vertex. I consider AB as the base because it is represented by the force P. Therefore, P is represented by the side AB, the base of the triangle, and in the triangle AOB, the vertex is represented as the moment center. Therefore, the moment of the force P about the point O will be twice the area of the triangle ABO. That is what we just learned from the graphical representation of moments. That is what we just learned. Now similarly, make it equation 1. Now look at the triangle AOC. This is the vertex. I consider this as the base, which is represented by the force Q. So the moment of this force Q, which is represented by the base of the triangle AOC, that is AC. So the moment of the force Q about the point O, which is the vertex of this triangle, and Q is the base, will be 2 times the area of the triangle AOC. So that is what I am saying. For triangle AOC, O is the vertex, that is the moment center. Q is equal to AC, that is the base of the triangle. Therefore, the moment of Q about O will be 2 times area of the triangle AOC. Then come back to the triangle AOD. Then come back to the triangle AOD. If you consider this as base, point O is the vertex and that is the moment center, and the base is represented by the vector R, the resultant of P and Q. So the moment of this resultant R, which is represented by the base AD of the triangle AOC, will be equal to twice the area of the triangle AOD. So that is what I have written. So therefore, for triangle AOD, O is the vertex, R is equal to AD, the base of the triangle. Therefore, moment of the resultant R about O will be 2 times area of the triangle AOD. Now, what you have to prove is this plus this should be equal to this. Now, only a few minutes left to finish it. To prove 1 plus 2 is equal to 3. Now look at. Now from geometry, area AOD is equal to area ADC plus area AOC, right? But what is interesting is area ADC and area ABD, both areas they lie between the same parallel lines, means the height for both the triangles are equal, so the areas will be equal. So that is what I am saying here. Area ADC will be area ABD will be equal to area AOB. This is to be understood because if there are two parallel lines, means the perpendicular distance between them is fixed. So taking this as base, from here to here as base, if you construct a triangle like this or if you construct a triangle like this, both will have the same area, because area of a triangle is half base into height. So between two parallel lines, if you construct two triangles having the same base, both will have the same area. That is to be understood. Now look at now. So area AOD instead of area ADC, now I can write area AOB since they are between two parallels, and this remains as such, area AOC. Now what do? I multiply this side with 2 and this side with 2. So what do I get? 2 times area AOD is equal to 2 times area AOB plus 2 times area AOC. And 2 times area AOD, 2 times area AOD, 2 times area AOD, where this is the base and this is the vertex, is the moment of the force R, that is the resultant of P and Q about O. So the left side represents moment of the resultant R about the moment center O. And what does this represent? Let us look at the triangle AOB. In triangle AOB, this base represents the force P. This is the vertex, that is also the moment center. So this area, 2 times that, represents the moment of the force P about O. So this represents the moment of the force P about O. And let us see what does this represent in triangle AOC. In triangle AOC, this is the base, which is represented by the force Q. This is the moment center. So twice the area of this triangle AOC will be the moment of the force Q about O. So this is the moment of the force Q about the point O. So this is the moment of the force P about point O. This is the moment of the force Q about point O. And the sum of that is nothing but the moment of the resultant of P and Q about the same point O. So that is all about the most important theorem called Varignon's theorem, a French mathematician. And we'll use these concepts now to solve problems from engineering mechanics, problem set 2.6. So when you go to solving from problem set 2.6, you will be using this concept only. Thank you. Thanks a lot. Thank you.